Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel and today's topic of discussion is pneumatic flow control methods. Our objective is to examine meter in and meter out flow control methods in pneumatic systems used to control the speed of pneumatic actuators. What seems to be a recurring theme in the pneumatics playlist, pneumatic systems are very similar to hydraulic systems in many aspects, yet notably different in others, principally because the power transfer medium of choice central to pneumatic systems, air, is compressible and occupies different volumes at different pressure and temperature conditions. This leads to pneumatic cylinders sometimes popping into place or moving at different speeds when subjected to different loads. Actuator speed control in pneumatic systems is therefore a somewhat difficult, but not impossible task. Predictability is key. Given a constant load and constant input conditions, a technician should be able to dial in actuator speed to a reasonable degree of accuracy using flow control valves. Additionally, we'll examine more sophisticated systems, making use of closed-loop control and proportional valves in much later lectures. Today's lecture features the relatively primitive, yet highly effective flow control valve with check valve bypass. As the title implies, a flow control valve with check valve bypass has two parts. One, a flow control valve, which is a manually adjustable restriction. Tightening the restriction reduces flow and reduces actuator speed. In contrast, opening up the restriction increases flow and increases actuator speed. The second part, the check valve bypass in parallel to the restriction orifice, determines in which direction flow is metered or controlled. In one direction, the check valve poppet is forced to the seat and forces flow through the restriction orifice. In the reverse direction, the check valve opens and allows unrestricted flow. Because flow control valves with check valve bypasses are orientation dependent, manufacturers often indicate direction of controlled flow using an arrow. Alternatively, one might see a big arrow pointing in the unrestricted direction and a small arrow pointing in the controlled direction. Install it in the wrong place and the wrong orientation, and you'll get wrong results. Before we discuss meter in and meter out extension and retraction configurations, it might be helpful to quickly review how double-acting cylinders extend and retract. Not all the time do you want cylinders extending and retracting with the speed of a Mike Tyson punch-out, and sometimes it may be necessary to slow down one or both actions to meet the needs of an application. Extension is two simultaneous actions and necessitates two ports for a double-acting cylinder. 1. Pressurized flow must enter and fill the cap end. And 2. The rod end must be exhausted to the environment. Similarly, retraction is two simultaneous actions and necessitates two ports for a double-acting cylinder. 1. Pressurized flow must enter and fill the rod end, and 2. The cap end must be exhausted to the environment. This allows us two opportunities to control extension and two opportunities to control retraction. To control extension, we could restrict flow coming into the cap end. The slower the cap end fills up, the slower the cylinder will extend. This is known as meter-in extension. Option 2. Alternatively, we could restrict flow coming out of the rod end. The slower the rod end drains, the slower the cylinder will extend. This is known as meter-out extension. The same things could be said about retraction. To control retraction, we could restrict flow coming into the rod end. The slower the rod end fills up, the slower the cylinder will retract. This is known as meter-in retraction. Alternatively, we could restrict flow coming out of the cap end. The slower the cap end drains, the slower the cylinder will retract. This is known as meter-out retraction. This yields four different methods of actuator speed control: meter-in extension, meter-out extension, meter-in retraction, and meter-out retraction. As easy as this general concept may be, the difficulty in implementing these four different methods is installing a flow control valve with check valve bypass in the proper location and the proper orientation. You'd be surprised how often people mess this up under stress. Here's my advice. Pay attention to the check valve, since it is the single component that determines the restricted and unrestricted direction of flow. Let's examine all four methods, starting with meter-in extension. A meter-in extension arrangement makes use of a flow control valve with check valve bypass installed in the cap end, oriented in the following fashion. When flow enters the cap end, it forces the check valve poppet to the seat, and all flow must travel through the narrow restriction orifice. Closing the orifice slows the extension speed down. Opening up speeds it up. The check valve bypass allows the cylinder to retract at full speed. During retraction, air exhausted from the cap end pushes the check valve poppet off its seat, such that flow is unimpeded. Here's an example of meter-in extension. With the flow control valve relatively wide open, the cylinder darts out like the head of a hungry snapping turtle. Let's dial that down a bit. A couple turns in the flow control valve knob narrows the restriction orifice. The cylinder extends a little slower. A couple more turns of the flow control valve knob narrows the restriction orifice even more, and the cylinder extends a little bit slower. If we close the flow control valve all the way, nothing reaches the cap end, and the cylinder doesn't extend at all. Let's open it back up. After a bit of fiddling with this, a technician can dial extension speed into a desired range. You note retraction speed remained unaffected using a meter-in extension configuration, since the check valve bypass ensures air exhausted from the cap end during retraction is unimpeded. Additionally, note I kept the load constant with this application. If I unloaded or increased the load, the pressure necessary to extend should change. Any change in pressure means compressible air occupies more or less volume. As a result, the cylinder would move slightly faster or slower. If, however, I loaded the cylinder back up to the previous specification, it should return to the previous extension speed. This is all one could reasonably hope for given this level of sophistication. Since subtle real-time variations in extension speed may have escaped your notice in the previous live action demonstration, here's a simulation in Automation Studio, making use of a handy plotting function for the numerically inclined. In this application, I'll be plotting rod displacement in inches as a function of time for a cylinder with a 10-inch rod. When I energize the solenoid with the flow control valve opened up to 0.03 inches in diameter, the rod reaches full extension in a matter of roughly 0.7 seconds. Note how steep the ramp up is since the rod is moving pretty fast. If I close the flow control valve restriction orifice down to 0.02 inches and again energize the solenoid, it takes about 1.5 seconds to reach full extension. Note how the ramp up is a little less steep than previously since the rod is moving a little slower. Also notice retraction time seems to be unaffected because the check valve bypass allows unrestricted flow in the opposite direction. If I further decrease the flow control valve restriction orifice down to a super tiny 0.01 inches and again energize the solenoid, it takes an agonizing 6+ seconds to reach full extension. One could fiddle with the size of the restriction orifice to dial it to the desired speed. The plotting function in Automation Studio sure beats the dodgy feedback of standing there with an old school stopwatch. Let's now take a look at meter-out extension. A meter-out extension arrangement makes use of a flow control valve with check valve bypass installed on the rod end oriented in the following fashion. During extension, air exhausted from the rod end forces the check valve poppet to the seat, and all flow must travel through the narrow restriction orifice. Closing the orifice backs up air in the rod end, thus slowing extension speed. As previously, the check valve bypass allows the cylinder to retract at full speed. During retraction, air entering the rod end pushes the check valve poppet off its seat such that flow is unimpeded. Here's an example of meter-out extension. With the flow control valve relatively wide open, the cylinder again darts out with a bang. Let's dial that back. A couple more turns in the flow control valve knob narrows the restriction orifice even more, and the cylinder extends a little bit slower. All right, here's a question that really highlights some of the variances between hydraulic and pneumatic systems. What would happen if I close the flow control valve all the way in a meter-out extension configuration such that no air could leave the rod end? Would the cylinder move at all? Think about it. I'll give you till a count of 5 to come up with an answer. 1, 5. Did you see that? The cylinder partially extended, even though the completely closed flow control valve on the rod end won't let any air escape. Why did it partially extend? I'll tell you why. Air is compressible. As pressurized flow enters the cap end, it compresses the air trapped at the rod end into a smaller volume, and the cylinder partially extends. Like I said earlier, pneumatic systems exhibit noticeable differences between almost identically configured hydraulic systems. Let's open it back up. After a bit of fiddling with this, a technician can dial extension speed into a desired range. As previously, you'll note retraction speed remained unaffected using a meter-out extension configuration, since the check valve bypass ensures air entering the rod end during retraction is unimpeded. Let's now take a look at meter-in retraction. A meter-in retraction arrangement makes use of a flow control valve with check valve bypass installed on the rod end oriented in the following fashion. When flow enters the rod end, it forces the check valve poppet to the seat, and all flow must travel through the narrow restriction orifice. Closing the orifice slows the retraction speed. The check valve bypass allows the cylinder to extend at full speed. During extension, air exhausted from the rod end pushes the check valve poppet off its seat such that flow is unimpeded. Here's an example of meter-in retraction. With the flow control valve relatively wide open, the cylinder jumps back like a frightened coyote into its guarida. Let's dial that down a bit. A couple turns on the flow control valve knob narrows the restriction orifice and reduces flow entering the rod end. The cylinder retracts a little slower. A couple more turns on the flow control valve knob narrows the restriction orifice even more, and the cylinder retracts a little bit slower.
All the way closed.
If we close the flow control valve all the way, nothing reaches the rod end and the cylinder doesn't retract at all. Let's open it back up. After a bit of fiddling with this, a technician can dial retraction speed into a desired range. You note extension speed remain unaffected using meter-in retraction configuration, since the check valve bypass ensures air exhausted from the rod end during extension is unimpeded. Finally, let's take a look at meter-out retraction. A meter-out retraction arrangement makes use of a flow control valve with check valve bypass installed in the cap end oriented in the following fashion. During a retraction, air exhausted from the cap end forces the check valve poppet to the seat and all flow must travel through the narrow restriction orifice. Closing the orifice backs up air in the cap end, thus slowing retraction speed. As previously, the check valve bypass allows the cylinder to extend at full speed. During extension, air entering the cap end pushes the check valve poppet off its seat so that it flows unimpeded. Here's an example of the meter-out retraction configuration. With the flow control valve relatively wide open, the cylinder slams back. Let's dial that down a bit. A couple more turns in the flow control valve knob narrows the restriction orifice even more, and the cylinder retracts a little bit slower. After a bit of fiddling with this, the technician can dial retraction speed into a desired range. As previously, you'll note extension speed remained unaffected during a meter-out retraction configuration, since the check valve bypass ensures air entering the cap end during an extension is unimpeded. At this time, you might be under the impression that meter-in and meter-out are equally applicable for all scenarios. This is not true. You'll note in the previous examples, we were moving a supported object laterally. There exist tipping, tilting, negative, or overrunning loads that preclude certain configurations, the classic example being a vertically lifted object. Consider a vertically mounted pneumatic cylinder that lifts on extension and lowers on retraction. Extension is not an issue. Either a meter-in or meter-out extension method work equally well. Retraction, however, that's the issue. You don't want the load to crash to the earth. We've got two choices, meter-in retraction or meter-out. Meter-in won't work, meter-out will. Allow me to demonstrate. A meter-in retraction does control flow entering the rod end. However, with no restriction on the cap end, as soon as the cap end is exhausted to atmosphere, the load slams to the ground. Not exactly the best load handling system if you wanted to keep the load in any usable state. In contrast, a meter-out retraction configuration keeps a cushion of air trapped in the cylinder cap end supporting the lifted load during descent. The tighter the restriction, the slower the cap end drains and the slower the descent. When in doubt, meter out. Let's try this with a different mounting configuration. Consider a vertically mounted pneumatic cylinder that lifts on retraction and lowers on extension. In this scenario, retraction is not a problem. Either meter-in or meter-out retraction methods will work equally well. Extension, however, is the issue. As previously, we've got two choices, meter-in extension or meter-out. Meter-in won't work, meter-out will. Allow me to demonstrate. A meter-in extension does control flow entering the cap end, however with no restriction on the rod end. As soon as the rod end is exhausted to atmosphere, the load slams to the ground and breaks into 1,000 tiny pieces. Let's try meter-out. In contrast, a meter-out extension configuration keeps a cushion of air trapped in the rod end supporting the lifted load. The tighter the restriction, the slower the rod end drains and the slower the descent. Again, when in doubt, meter out. Now that we've got a good appreciation for meter-out flow control methods, I should mention cylinders with adjustable cushions on extension and retraction make use of this method at the very end of the cylinder stroke. Cushions allow a cylinder to move quickly through a majority of its stroke, however ease it to a nice gentle stop at the limits of extension or retraction instead of just slamming to a halt. Cylinders with cushions have a special shaped piston with a plug that fits into a circular depression. Here I'm illustrating a cushion on retraction in the cap end with the rod omitted for clarity. As the piston retracts mid-stroke, the plug and hole don't come into play, and exhausted air has an unobstructed path out of the barrel. However, as the piston nears the limits of retraction, the plug fits into the hole, blocking the larger port, leaving a cushion of air trapped between the piston and the ring, with a narrow restriction as the only means for air to exhaust. If the cushion is adjustable, a technician can increase or decrease the size of this restriction so that the cushion of air is exhausted quickly or slowly, thus saving the piston face from repeated forceful impacts at the limits of extension and retraction. Lastly, I should mention that one can use a combination of methods to control both extension and retraction. Consider one such possibility, with two flow control valves with check valve bypasses, both installed in the cap end of a cylinder. Flow control valve 1 establishes a meter-in extension arrangement by forcing all flow entering the cap end during extension through the narrow restriction. During extension, flow control valve 2 would be bypassed. One would adjust flow control valve 1 to dial in extension speed. Flow control valve 2, in contrast, establishes a meter-out retraction arrangement by forcing air exhausted from the cap end during retraction through the narrow restriction. During retraction, flow control valve 1 would be bypassed. One would adjust flow control valve 2 to dial in retraction speed. Alternatively, one could put a flow control valve on either end of a double-acting cylinder. In this configuration, flow control valve 1 on the cap end establishes a meter-in extension arrangement, whereas flow control valve 2 on the rod end establishes a meter-in retraction arrangement. If one kept the flow control valves with check valve bypasses in place, yet flip-flop their orientation, you'd flip-flop their function. In this implementation, flow control valve 1 on the cap end establishes a meter-out retraction arrangement, whereas flow control valve 2 on the rod end establishes a meter-out extension arrangement. You may wish to pause the lecture and stare at these different configurations to discern the differences if they're not immediately identifiable. Again, check valve orientation is what determines the direction of a controlled or metered flow. Lastly, I should mention flow control is a good and often necessary thing. However, there are applications where one action must be precise and controlled, and the opposite action must occur as fast as possible. For example, consider some high-paced production process where extension must be slow and controlled. However, retraction needs to happen as fast as possible because another part's getting slammed into place. For this style application, one might consider a meter-in extension arrangement as long as we're laterally manipulating a supported load. On extension, flow entering the cap end would be forced through the flow control valve. However, during retraction, the check valve bypass would open and allow unrestricted reverse flow. You'd think the term unrestricted reverse flow would allow the most rapid retraction possible, but it doesn't. Principally because air exhausted from the cap end during retraction still has to travel through all the tubing to the exhaust on the directional control valve. Which begs the question, why are we worried about porting exhaust air back to a directional control valve if we're just going to dump it into space anyways? Why can't we just dump it into the atmosphere at the point of use? Wouldn't that accelerate retraction? Indeed it does. We'll examine a component called a quick exhaust valve in an upcoming lecture that allows this ability to selectively dump exhaust air directly into the environment at the point of use, thus rapidly accelerating one action of a complete reciprocation cycle. Until then, this concludes this lecture. In conclusion, this lecture took a look at pneumatic flow control methods, including meter-in extension, meter-out extension, meter-in retraction, and meter-out retraction. Additionally, we examined applications of these methods and discussed scenarios appropriate for and inappropriate for their use. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.